In this video, we are going to look at the ideal gas law, and we'll be thinking about it at the level of a freshman level Gen Chem class. So the postulates of the kinetic molecular theory of gases are as follows. Number one, a gas consists of small particles, so that would be atoms or molecules, that move randomly with high velocity. So these are always moving inside the container. The attractive forces between the particles of gas are usually very small, and so in the ideal gas, they can be ignored. We essentially say that the gas molecules or atoms or particles of any kind don't actually interact with each other. Number three, the actual volume occupied by gas molecules is extremely small compared to the volume of the container in which the gas is held. And so we think of the particles as point particles, meaning they have zero volume. So that's illustrated down here in number three. We see that if we took all of the gas particles and condensed them down so that they're all right next to each other, it's only going to take up a very tiny amount of the volume in the container here. And so they spread out by just moving around constantly. Number four, gas particles are in constant motion, moving rapidly in straight paths. And in the ideal gas law, we assume that they only turn when they hit the sides of the container, and this is done in perfectly elastic collisions. And number five, the average kinetic energy of gas molecules is proportional to the Kelvin temperature, and it has to be the Kelvin temperature. That's the temperature scale that we're going to be using for pretty much everything in thermodynamics. And this postulate here is why we have to do that, because this only works when we're talking about the Kelvin temperature. And so the ideal gas law is this. So it's just the pressure times the volume equals the number of particles times the gas constant times the temperature in Kelvin. Or to put it short, PV equals nRT. The state variables we're thinking about here are the pressure, which has a bunch of different types of units. I'm not going to go through all of these here, and these are not even all of them. One thing in a general chemistry class especially that professors seem to like doing is giving people problems where you have to do conversions, usually of the pressure units. Then the volume, which is the V here, and these can have multiple different types of units. Mostly what you see in thermodynamics are using the liter or the cubic meter, but you can also see it with milliliters or cubic centimeters. Then the temperature, as I said, we're pretty much always going to be using Kelvin. If you want to convert from degrees Celsius to Kelvin, then you can just add 273.15. Then the amount is pretty much always going to be in moles. This can also be in mass, which can be converted to moles using the molar mass. Then the gas constant, which has a ton of different variations depending on what units are used. In something like this, these are often the units on our gas constant R. And so if we look at each of these in a little bit more detail, when we talk about the pressure, what we mean is that the pressure is the amount of force exerted on the surface of a container. And in particular, we're going to be thinking about the internal surface of the container. And so it's just the force over the unit area. And so that looks like this, where we have this gas that's a bunch of particles inside this container. And so when the particles get up near the wall, they run into the wall, and that is imparting a force on the wall. And so when you have tons of these particles doing that inside the wall, then that's exerting a pressure on the inside of the wall. And so we see that if we have the F equals ma, where F is the force, m is the mass, a is the acceleration, then increasing the amount of stuff, that's the m and the ma here, or the amount of energy or temperature, which would increase the velocity at which the particle runs into the wall, which when it bounces off of it is going to have an acceleration, and so the acceleration is going to be proportional to the energy slash temperature of the gas. And so if we increase that, we're increasing the A here, then this will give us higher pressure because we're increasing the force. So remember, the pressure is the force per area, so if we increase the force here, that will increase the pressure. Similarly, reducing the surface area, so that would be the A here, by reducing the volume of the container will also increase the pressure. So if we had this container here, we don't change the number of particles. If we just reduce the volume of the container by a certain amount, then that reduces the area of the container on the internal surface here, and so that will increase the pressure. We can essentially think about it as now we would have the same number of particles. If there is less volume, they're going to be running into the walls a lot more, and so that's going to exert a pressure on the inside walls. The other thing we want to remember is that the pressure and volume of the system are just the sums of the partial pressures and the partial volumes of the individual components. This is known as Dalton's law when we're thinking about pressure, and Avogadro's law when we're thinking about volume. For volume, I think it's pretty straightforward. If you have 4 units of volume, you add them up. That means you have a volume that is 4 times what each of those smaller volumes are. But Dalton's law tells us that this works for pressure as well. So for air, we have 101.3 kilopascals. That can be obtained by just adding up the partial pressures of each gas that make up the air. And so the total pressure is just the sum of all the partial pressures. Then if we look at the gas constant R, this is actually obtained by just taking Avogadro's constant, that's N sub A, and multiplying by the Boltzmann constant, which is just a conversion between temperature and energy. So we just take those two constants here, we multiply them together, and that gives us our gas constant right here. And so this is the gas constant in units of joules over mole times Kelvin, but this can be interconverted, as I said, into a ton of different values just depending on what the units are. So if we take our R here being equal to this gas constant in terms of the joules over mole Kelvin, we can do a bunch of dimensional analysis, which you can go through here if you want. And that gets us to this right here, which is the version of the gas constant that's going to get used most often when we are talking about the ideal gas law. Then if we look at temperature, remember this is part of postulate 5 from our gas law postulates, and this is just that the average energy is proportional to the temperature here. And in fact, the average energy will be equal to 3/2 times the Boltzmann constant times the temperature, where the 3/2 here just comes from what's called the equipartition theorem, which we're not going to get into here just yet. We'll talk about that more in future videos when we start drilling down more on the thermodynamics. Also, we can show that the temperature is the number of particles with a particular kinetic energy in a Maxwell-Boltzmann distribution. So essentially what this is telling us is that the area under these curves is the number of particles, and so we can see at the lower temperature, most of the particles are in this lower energy right here. When we're at the higher temperature, then we have more particles at the higher temperatures right here. If we have a system with n moles of particles at some time t equals 1, then we have P1, so that's the pressure at time 1, times V1, that's the volume at time 1, equals nR, and then that's times the temperature at time 1. And so we can say, after some rearranging, that the P1 V1 over T1 will be equal to N times R. So remember, we're holding N constant, then R just is a gas constant. So we're saying that this is going to be equal to some constant, the number of particles times the R constant right there. Then if we have the same system of N moles of particles at some future time t equals 2, where the pressure, volume, and or temperature may have changed, but the number of particles remains the same, then we would have P2 times V2 equals NR times T2. After rearranging, we see that this is still equal to the N times the R here. So that means we can set both of them equal to the N times the R. Then if we just remove this N times R here, we see that it's P1 V1 over T1 equals P2 V2 over T2. And this is called the combined gas law right here. We see from the combined gas law that if we then just hold the temperature constant, we get what's called Boyle's law, which is just P1 V1 equals P2 V2. And we can see this pictorially here. So if we increase the volume, then we're going to have lower pressure. Then if we reduce the volume, we're going to increase the pressure. So when we reduce the volume, remember, we're reducing the surface area on the inside. And so those same number of particles are going to be running into the walls more often. There's going to be more force on the inside. And so that's going to increase the pressure. But if instead we hold the pressure constant, then the combined gas law would yield us what's called Charles's law, which is just V1 over T1 equals V2 over T2. And so we can see that if we heat up the gas, for instance, this is going to increase the volume, whereas if we cool down the gas, this is going to reduce the volume. You may have noticed this, for instance, in the winter, that your tires become less inflated. This is because they're cooling down. This is going to reduce the volume inside your tires. Instead, Instead, if we hold volume constant, then we get what's called the Gay-Lussac's law, which is P1 over T1 equals P2 over T2. So we can see here we're holding the volume constant. If we heat this up, then we're going to increase the velocity of the particles inside. They're going to hit the walls with more force, and so that's going to increase the pressure. Whereas if we let it cool down, then that's going to reduce the pressure. Now, if we say that the amount of stuff N here is not constant, so N sub 1 is not equal to N sub 2, but we hold the pressure and the temperature both constant, then we get what's called Avogadro's law. And so this is just relating the amount of stuff to the volume that it is occupying. If we have more stuff, it's going to occupy more space. If we have less stuff, it's going to occupy less space. So when we have the temperature T held constant and we reversibly, and we'll talk more about what that means in future videos, vary the volume, then we get what is called a pressure volume isotherm. So different temperatures will have their own isotherm. So we see here at some low temperature, this line right here would be our isotherm. So we are varying the volume and seeing what happens to the pressure here. Then we can increase the temperature until we get up to here. Then this will be our isotherm. This will be what happens to the pressure as we adjust the volume. And we can actually calculate the amount of work we do by moving across an isotherm by just taking the integral of the pressure times the change in the volume here. Again, we'll talk more about what all that means in future videos, but this is just a sneak peek about what we're going to be talking about in the future. Now, if instead of the pressure and volume, we have the temperature and pressure, we can obtain what's called a phase diagram, which tells us what phase a particular substance will be in given a set of pressure and temperature. So we can see on this horizontal axis, we're just varying the temperature. On the vertical axis, we are varying the pressure. We can look at this for a couple of different things here. For water, it looks like this, where we can see if we are down in this range here, so under this red line right here, those pressures and temperatures will give us a gas. If we are up in this region right here, then it is a liquid. If it's over here, then it's solid. For water, one thing to notice is that this line right here actually has a negative slope, and this actually comes from the fact that water expands when it freezes. So if we look at this for carbon dioxide, we immediately see that this line has a positive slope, and that's because the solid form of carbon dioxide is less dense than the liquid or gas forms for it. But anyway, that was all of the general chemistry level of gas stuff that I wanted to talk about. This is important for understanding thermodynamics, since in thermodynamics we often talk about things in the gas phase, since the gas phase tends to be a bit easier to work with. We will, of course, talk about things in the liquid and solid phases, but like I said, in a lot of, especially early thermodynamic stuff, we are often talking about things in the gas phase. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.